New in version 21 of LUSAS is the Pedestrian Moving Load Analysis tool. Now this allows me to choose a design code and set up a pedestrian or group of pedestrians moving across the bridge with a given force and speed. Now in this analysis I've already set up a linear static analysis and I've also set up an eigenvalue analysis. So if I load up the results, we're looking at the self-weight case, the dead load deflections. But if I set active the first eigenvalue, this is mode 1, if I rotate this around, you'll see that this is a lateral mode and has a frequency of 1.6 Hertz. If I set active mode 2, and again rotate the model around slightly, you'll see this is a vertical mode and it has a frequency of 3.05 Hertz. Now these frequencies are important because we'll check these against the design code. Now in this case we're going to be using the Eurocode National Annex, and the comfort criteria are set out in clause 244. Now there's two checks in the vertical direction that we're going to do. 2444 is the moving pulsating pedestrian or group of pedestrians, and that's what we'll use the new analysis tool to set up. The check under 2445 is a crowded state, and that's fairly easy to set up using just the traditional transient dynamic case. Now the comfort criteria are set out in 2446, and these will give me an acceleration limit that I need to check against the analysis model to see whether the bridge is okay. Within clause 2446, for a fundamental frequency of less than 5 Hertz, you can work out an acceleration limit, and that acceleration limit you have to prove that the analysis model is below for the structure to be safe. Now, in terms of the analysis tool that we're using, this is going to set up the analysis in accordance with 2444. So it'll be a single pedestrian or group of pedestrians moving at a pulsating force across the structure at a given speed. Now, as well as the vertical pulsating load, you can add an additional lateral or axial component to the vertical component to try and maximize the accelerations that you're seeing on your structure. But this is optional. Now, to set up the analysis, I'm just going to switch off the results. I'm going to switch back on my geometry layer, and I'm going to create a line. Now that line will form the direction that the pedestrians are going to take, and I'm going to create the line longer than the structure at both ends. And in this example, I'm just creating the line down the middle of the structure. Now there's no real guidance in the Eurocode where this line should be, so you might want to try down the middle to one side and see what creates the worst behaviour. Once you've created that line and selected it, I can go to the bridge menu and I can select the Pedestrian Moving Load Analysis tool. Now the first thing I'm going to do here is define the load. So if I go to New, I can choose which design code I'm working to. Now certain design codes have pedestrian criteria, some don't. Now, you can use one of the codes or you can create your own custom definition, but I'm going to use the UK National Annex, the latest version of the Eurocode. And the first thing I'm going to do is choose whether I'm going to look at walking pedestrians or jogging. I'm going to look at jogging. Next, I set the bridge class. So I'm going to go for class C, which is a bridge in an urban environment. I then set the fundamental natural frequency, so this is the 3.05 for the vertical mode that I showed you earlier, and the reduction factor I'm going to leave as 0.8. Once you've done the vertical definition, you can add an additional lateral or axial component. Now these aren't defined in the Eurocode, so we've come up with some expressions to apply additional forces. So I'm going to put some lateral force as well here. And as I showed you earlier, there's slightly different sine waves from the vertical and the lateral. Okay, I'm going to give this a name, just pedestrian load. and I'm back to the moving load dialog. So in here, I can choose the search area. I've got a search area on my structure, which I call deck. And I can then set the number of time steps that I want, so the time interval. Now I'm setting the time interval as 0.005 of a second, and that's going to give me just over 2,000 time steps in the analysis. Once you're happy, I press OK, and it will build the analysis model for me. So you can see the taskbar going across the bottom there, setting up the 2,266 time steps. So there's my analysis model. And you can see all the time steps there. Now, before I run this, I want to add a steel property, a steel material that has damping on it, because the basic linear static analysis model was just linear steel, but I want steel with damping. So I'm going to select all the bridge members. I'm doing that by just selecting the thick beam elements, and I'm going to assign the steel with damping. And I'm going to assign that into the pedestrian moving load analysis. Okay, so that's set up the model. I'm now ready to solve the problem. Now this is going to take some time because of the 2,000 time steps. So essentially what we're going to do is we're going to fade out and then fade back in once I've got all my time steps loaded up. Okay, so this is now solved. Now I'm going to select the node at the quarter span here, and I'm going to use the graph wizard to do a graph. Now the graph that I'm going to do is a time history graph. I'm going to look at named and response time. So there's the response time. And in the Y direction, I'm going to look at nodal, and I'm going to look at the vertical displacement to start with. Now I'm just going to label up the axes here, so response time and displacement. Now at the moment I'm going to leave the show symbols on, and you can see where it says show symbols you get a big dot on the graph, so I don't particularly like that. So we're going to do another graph. This time we're going to look at acceleration, so that should be the same. So named, I'm going to look at the acceleration component, and I'm going to look at the vertical component, AZ. I'm going to change that to acceleration from displacement. And this time I'm going to switch off the show symbols. Okay, so there's my graph. It's a bit difficult to see, so I'm just going to edit the graph and make the curve thicker. So there's my acceleration graph. Now, what I can do now is look at this peak acceleration. For this, it's coming in as about 0.93 meters per second, and I can compare that against the design code criteria limits, and for this particular structure, that works out as 1 meter per second. So I've analysed the structure, I've proved that it's working in accordance with the code.